5, Physics chapter 5, and our today's topic is stretchy forces. Okay, we'll be looking at generally the effect of forces, but in this segment of the effect of forces, we'll be looking at stretchy forces. Okay. Stretchy forces, and in looking at that, we're going to be using a spring. We're going to be using a spring to test this concept in physics. Okay, and we're going to look at the experiment done by Robert Hooke, like over 350 years ago. The experiment someone did. His name is Robert Hooke, a scientist. So we're going to see what he did that time, and we're going to see the effect of that. But before we move on, let's quickly take a look at our tutorial.
This video is about Hooke's law and the associated practical. Hooke's law states that the extension of an elastic object is directly proportional to the force applied, up to the limit of proportionality. What does this mean? Objects can be compressed, made shorter, or extended, also known as stretched, so made longer. An elastic object is an object that will return to its original shape when stretched. This is called elastic deformation. The most common examples you will come across are springs and rubber bands. Materials such as plastic do not have elastic properties because when extended, they do not stretch but instead break. This is called inelastic deformation. When two quantities are directly proportional to each other, as one increases, the other does too by the same factor. When more force is added to extend the spring, the extension increases too. It is often that masses on a hanger are applied to the end of the spring. This creates the force for the extension. The limit of proportionality, also known as the elastic limit, is the point at which force and extension are no longer proportional. The material will no longer return to its original shape. It is described as permanently deformed. This is what happened to the spring on the right. It is broken. Hooke's law can also be described by the equation F is equal to Kx, where F is the force applied to the spring in newtons, and K is the spring constant, which is a measure of the stiffness of the spring in newtons per meter. The stiffer the spring, the bigger the value of the spring constant. X is the extension of the spring when under force F and is measured in meters. In class, you may have completed this practical, analyzing the relationship between the force applied to the spring and the extension. In this experiment, the independent variable, the variable that you will change, is force. You will change this by adding masses to the mass hanger on the end of the spring. The dependent variable, the variable that will change as a result of changing the force, is the extension of the spring. The following equipment is needed and should be set up as shown in the diagram: clamp and stand, ruler, spring, mass hanger, the hanging frame with a hook used to place masses onto, masses, and then a pointer. Using the pointer adds a control variable to reading the length of the spring. It is always read from the same point every time. The experimental method is as follows. Set up the equipment without any mass hanging from the spring. Align the marker to a value on the ruler. Record this as the original length of the spring. Add the 100-gram mass hanger onto the spring. Record the mass in kilograms and the position in centimeters from the ruler. Now that the spring is extended, use the pointer for accuracy. Add another 100 grams to the mass hanger. Record the new mass and position from the ruler now that the spring has extended further. Repeat this process until at least 5 masses have been added. An example table of results looks like this. Hooke's law states that the force is proportional to extension. So the weight or force applied by each mass needs to be calculated. Using Newton's second law, force is equal to mass times gravitational field strength. The experiment should be repeated at least 3 times, so the 3 lengths are recorded in the table. So the average length must then be calculated. The extension is found by subtracting the average length from the original, the length of the spring without any mass. The next step in the experiment is to plot a force extension graph. You will see examples of this graph with force and extension on either axis. Both ways are correct. Plot each point with a cross. Draw a line of best fit using a ruler, where there needs to be an equal number of points equidistant above and below the line. In this worked example, a diving board spring is extended by 20 centimeters when a 500 Newton force is applied to one end. Calculate the spring constant of the spring for 2 marks. Record and rearrange the equation for Hooke's law. F is equal to kx. So when we rearrange, we divide both sides by x to get k by itself. So k is equal to F over x. Now substitute the known quantities into the equation. So k is equal to 500 divided by 0.2, where 0.2 meters is 20 centimeters for 1 mark. Now calculate the final answer. K is equal to 2,500, where the units for K are newtons divided by meters for the second mark. Make sure you show each step of your workings clearly. In summary, Hooke's law states that the extension of an elastic object is directly proportional to the force applied, up to the limit of proportionality. Forces applied to an object cause it to either compress or extend. When extended, objects can deform elastically or inelastically. Force and extension are directly proportional to each other, which means that when more force is added, then the length increases by the same amount. Objects that extend beyond their limit of proportionality do not extend according to Hooke's law. Don't forget to check out all our other fantastic revision resources. Here.
Okay, so this is a brief tutorial to what we have today. So most of the things has been covered by the tutorial. The tutorial started by looking at, you remember we said this section of chapter 5 is stretchy forces, right? We want to be looking at stretchy object or stretchy forces. So this is chapter 5, part 1. We can call it 5, part 2. Okay, chapter 5, part 2. Okay, so here, the first thing we do is to look at stretchy objects. Good example is a spring. Okay, a good example is a spring. Another example is our rubber band. You know, the rubber band we used to hold things, we used to hold money, we used to hold things. It's a stretchy object. Now, object, depending on the kind of force we apply to it, determines which kind of deformations or which kind of change in shape that will happen to the object. For example, if I have a plastic material, if I have this as a plastic material and I apply two forces to it, one coming in like this, pressing it, and another force also pressing in from this side, then what will happen to this object? The object will compress. The object will compress. So if you take a spring and you bring the spring, you press it against itself from both sides. You press the spring against itself from both sides, the spring will compress. So this will be compressional forces. The force that will be acting here will be called compressional force. Okay? Then what if we take the same object and we apply force stretching it out? We apply force stretching the object out. For example, if we apply force to be pulling it out this way, not pressing it together, but to be pulling it apart, this will be torsional force. The force acting here will be torsional, will be a torsional force. Okay? Torsional force will be happening. So materials that can be stretched can be stretched in different direction or in different orientation. It could be torsional, it could be compressional, depending on the way the force is being applied to the material. So if you pull a spring apart, if you're pulling it apart, you apply a torsional force, and if you pushing it against itself, you apply what we call the compressive force. Is that okay? Now this is the first thing we know, and these objects, they can deform when they go beyond the limit of their proportionality. What do we mean by limit of proportionality? They can deform when they go beyond the limit of elasticity. You know, everything that that is elastic has a limit upon which you can stretch it. It has a limit upon which we can stretch it. If we go beyond the limit of its elasticity, the object will deform, meaning we no longer obey Hooke's law. This proposition or this concept was arranged by a scientist called Robert Hooke in more than close to 400 years ago. So you can imagine what we are asking you to learn now was even discovered by someone close to 400 years ago. So you shouldn't feel this is too much. Okay? So now the point is, what he did was that he alluded that the stretching force and the corresponding extension that is produced, they are in proportion. As long as you have not gone beyond the limits of elasticity of that object. For example, let's take a look at a spring. What he said is that if this is an original spring that is hung on any material, on a rector stand, you hang a spring here on this material, we can measure the original length of this object. We can take the original length of the object, okay, and take the dimension of the original length of the object, okay. We can take note of this original length, and we call it original length. We call it original length, this one. So we can call it L naught, the original length of the object. Then he said this object can be stretched based on the additions of masses. You know, force and mass, they are in relation, because force is equal to mass times acceleration, or mass times acceleration due to gravity. But because this has something to do with weight, we'll be using G instead of A. Okay, this force is like weight. Okay, weight. You know, weight is a force, a vertical force. Okay, force that is pulling an object downward. Okay, so we'll be using G instead of using A. The same concept somehow. This one is acceleration due to gravity, while the other one is horizontal acceleration. So for this particular experiment, or for this particular explanation, let's use G. Now, if you add mass, gravity is a fixed value. For Igsce, we take a value like 10 approximately. We say G equal to 10 Newton per kilogram. 10 Newton per kilogram for G. Okay, we take this as an approximation for our Igsce concept. Now, every mass you add, let's say you add 1 kilogram of mass or 1 gram of mass, you multiply by 10. So that will be 10 Newton. You get the force, or you get the weight, as the case may be. Now, according to Robert Hooke, he said that anytime we add mass to this, the force is proportional to the new length that is produced. You know, a new length. When you didn't add anything, you get the original length. Now you have another length. You can call it L final something. Now to find extension, extension is the difference between the whole new length minus the original length. So our extension, according to Robert Hooke, he said if you want to find the extension that is produced, the extension is equal to the new length, or whichever length you're looking at after this spring has been stretched, minus the original one. Minus the original length when you didn't add anything to the spring. Minus the original length when you did it. So this is the extension, the difference. After you added mass, you know the spring will stretch out a little bit more. So the difference between the original length of the spring and the new one, the difference is called the extension. The difference is called the extension. Now this is what Robert Hooke said. He said this extension, so permit us to be using X. Some textbooks they use E, some textbooks use X. So in this case, we'll be using X as our reference. Now, he said, this extension that is produced, according to Robert Hooke, he said is directly, let's use the symbol of proportionality. Okay, this is the symbol of proportionality. He said this extension that is produced is directly proportional to the stretching force. It's directly proportional to the force, meaning the weight in this regard now. Force means weight in this regard. is directly proportional to the stretching force. That's the force that is pulling it down, that is making it to stretch out. So he said they are in proportion. But provided that there is a condition, provided that the elastic limit has not been exceeded. What do we mean by elastic limit? The spring will continue to stretch out until it reaches its level of deformation, until it reaches a point where it can no longer stretch. And if you stretch it beyond that, it will deform. Meaning even if you remove the mass, the spring will no longer be able to return back to the original length. Normally, as you add mass, when you begin to take out the spring is stretched. When you add mass, it's stretched. When you add more mass, it's stretched more. He's saying that how much extension is produced is proportional to how much mass you are adding to it. If you add 2 Newton, let's say a force of 2 Newton, the extension will make, let's say the extension is 1 centimeter. If you add 4 Newton, the extension will become 2 centimeter. If you add 6 Newton, the extension will become 3 centimeter. They are in proportion. Like proportion the one you did in maths. Okay? So he's saying that if you have extension and force, if you add more force, the extension will be in proportion with the force you are adding. So let's say originally when force was 0, we didn't add any force. The extension was 0. There was no extension, right? It's just the original length, no extension. Now we had 2 Newton, then this one become 1 centimeter. This one we make it 4 Newton. This one become 2 centimeter. You see they are in proportion. Every increment, 2 increment here is 1 increment here. So the next one, if you have 6, here will be 3. So this is what Robert Hooke proposed, that the extension produced is directly proportional to the force that is applied to it. But provided there's a condition, provided the elastic limit is not exceeded. You've not passed the limit of proportionality of the spring. Every spring, if you continue to stretch it, it will reach a point that it can no longer come back if you stretch it beyond this limit. Even human beings, we have limits. If we stretch beyond limit, we get what we call high blood pressure, or we die. So this is, if you stretch beyond limit, everything has a limit upon which it can bear, it can take. So the spring also has the same. When you are stretching the spring, it will continue to stretch for you, and when you release it, it comes back to the original form. However, this is only holding when the spring has not gone beyond the limit of proportionality. If the spring goes beyond the limit of proportionality, even if you remove the load, force is called the load. We call it weight, we call it load, we call it force. Any of this language that is used is the same thing. When you begin to remove the load, or remove the mass, or remove the force, or remove the weight, the spring originally, if it has not gone beyond its limit of proportionality, it will return back to the way it was originally. But if it has gone, that means it's deformed. It can no longer. So according to Robert Hooke, he said, the extension produced is directly proportional to the stretching force, provided the spring has not gone beyond the limit of stretching, has not gone beyond the limit of proportionality. Is that okay? So that's what Robert Hooke explained, and this is what it is. Now he said, if you remove in mathematics, if you remove the symbol of variation or proportion, you have to introduce the constant. Right? We have to introduce the constant. So if we want to introduce the constant, we say this f is equal to, if you introduce equal to, you bring the constant. Constant is the spring constant is called K. The spring constant is called K. To remove the symbol of variation, we introduce the constant. The spring constant is K. And then we now have Kx. We now have what? Kx. Now, where is this K coming from? The K is the spring constant. Okay, this is the law. If they ask you to state Hooke's law, this is the law. You say Hooke's law states that the extension produced in elastic object is directly proportional to the stretching force, provided the limit of elasticity has not been exceeded, provided the object has not exceeded the limit of proportionality. Now, then you go further to remove the symbol of variation or symbol of proportion by introducing equality and putting the spring constant K. Constant K. Now, to find K, this K is a constant, right? Since it's a constant, it does not have one value depending on the object you are using. To find K, you make K the subject. K will be the force over the extension. You make K the subject of formula. This is mathematics in algebra. This is algebraic mathematics. So K is equals to the force over the extension. So if anytime we want to calculate extension, the spring constant, we use this formula. And the unit, the unit of force is Newton, and the unit of this is meter. So is either Newton per meter or Newton per centimeter. Either Newton per meter for K or Newton per centimeter. Now let's move on. We've explained this concept in details. We've also stated the law, right? That the extension in an elastic object is directly proportional to the applied force up to the limit of proportionality. That's Hooke's law. Okay, that's Hooke's law. So we should be able to state Hooke's law. We should be able to explain the experiment. We've given the mathematical equation. We say F equal to Kx, right? And then we say K is the spring constant that you calculate most of the time. Is the stiffness of the material, the stiffness of the spring. The stiffer the spring, then the more difficult it is for it to stretch out completely. Is that okay? Now let's go to the graph. Now let's show the graphical relationship of what Robert Hooke stated. According to Robert Hooke, he said when you plot, normally we plot the force on the vertical axis when you are plotting the graph, and you plot the extension on the horizontal axis. But however, you can put extension here and put force here. But the most common one, standard one, is plotting the force on the vertical, or the weight on the vertical, or the load. Please don't get confused. If you go to some textbook, the load here is the same thing. So load here, extension here. Now we plot a graph. We suppose if the spring obeys Hooke's law, then we're going to get a straight line relationship. We're going to get up to the limit of proportionality. Now here is the limit of proportionality. This is where, up to this point, from the beginning to this point, this is where every time we increase the load, the extension will increase. We increase the load on the spring, the extension will increase. That's what this graph is showing us. That you can see extension is increasing because it's going this way, this horizontal manner. And the force is increasing also because it's going up. This line is a depiction, it's an explanation of what is increasing in the horizontal direction and also increasing in the vertical direction. So as it starts from the origin 0 here, this is showing, as you're moving up this gradient, this line, is showing that the force is increasing because it's going up as well. The force is increasing and it's also going this manner. The extension is also increasing. Up to you get to the limit of elasticity. This is the limit of elasticity of the material. If you go beyond here, the object will deform. It will become a non-linear graph. This is a linear graph. Why is it a linear graph? Because it's in proportion. The force and the extension, are in proportion. They are in proportion. So meaning if you increase force, extension will increase up to this point. So in Cambridge IGCSE, here is called the limit of proportionality. Here is called what? Limit of proportionality. Up to this point, the spring has not deformed. The spring will still return to its original form. When you remove all the force, it will return back to the original form. Okay, original length. Now, if you continue to stretch the spring beyond this point, the spring will deform, will no longer obey Hooke's law. It will no longer obey Hooke's law, it will deform. It will go beyond this limit. It will no longer be able to return back to its original form. So this is called the deformation point. You can see it's now a non-linear graph. It's no more a linear graph. But from 0 to this level, is a linear graph, which means Hooke's law is being obeyed. So they can give you an exam and ask you which region obey Hooke's law from this graph, from this whole region. This is where Hooke's law is being obeyed. This is where Hooke's law is being obeyed. Okay? This is where Hooke's law is being obeyed. Okay? Beyond here, beyond this place, Hooke's law is no longer being obeyed. Okay? So this is the graph that explains that concept, the Hooke's law concept. Now let's talk about the gradient of the graph is the K, right? You know, right? The gradient is the K. Why? Why is the gradient the K? Look, the gradient is the K because we said K, let's change our color. We said K is a force over extension. K is force over extension. So logically, the change in y, which is the force axis, change in y, the change in y, you know gradient, right? We've studied gradient. So if I put this one as gradient, m, you know m for gradient in mathematics. So if we put it, it's the same thing now in this regard. change in y, like f2 minus f1, if you take 2 points on the graph, over change in x, or change in the horizontal axis, which is extension 2. If I choose 2 points, for example, this point and this beginning point, if we choose these 2 points, we want to calculate the gradient. Okay, if you trace this to the vertical axis, this will be your f2, right? This will be your f2. This will be your f2. Okay, this will be your f2. And the beginning will be your f1, this one, the beginning point. This will be our f1. Similarly here on the horizontal axis, this will be our x1. Okay, and this will be our x2 if you trace this one down. If you trace this one down, this will be our x2. This will be our x2. So why are we showing you this? What we are saying is that the spring constant is the gradient. The spring constant is the gradient. Why? Because gradient is, remember, it to be f2 minus f1, the vertical side. Gradient, which is the spring constant, so permit me to use k in this regard, which is the spring constant, is equals to the change, I'll just say change in f, which is f2 minus f1, over change in what? Change in y, and change in x, which is x2 minus x1. Change in f over change in x. So you get the gradient, which is the spring constant. So to calculate the spring constant is same like calculating the gradient of the graph. It's same like, that's the point I'm trying to make. It's same like calculating the gradient of a straight line graph. That's the spring constant. Is that okay? So let's move on. Let's move on quickly. Let's take a look at an example. Now we understand the definitions and the proportion, the explanation, the loading, and the law itself. Now let's take a look at the example. The figure below shows a force acting on a child who is balancing on a pogo stick. Now the child and the pogo stick are not moving. The child and the pogo stick are not moving. He's just standing on it and raising the hands. The spring will stretch out, then release it. It will come down, up, down, up, down. So it's the spring that is doing everything. The spring, compressed spring. This spring is so we use spring in making mechanical machines in many cases. Okay. Now let's take a look at it. Say the spring constant of the spring on the pogo stick is 4,000. Now in this question they've given us the spring constant. They're giving us the value. Okay, let's just circle it and call it K. So make it faster. Okay, so this is our K. They've given us our K value, 4,000, big value, 4,900 Newton per meter, right? Now, the weight of the child causing the spring to compress elastically from a length of 40 centimeter. Now they're giving us L1 from a length of 40 centimeter. This is X1. Okay, let's call it L1 so that we can calculate extension. L1 or L original, and to a new length of 33. This is the final length, L2. Okay, so the first thing we do is to calculate the extension, because this question did not give us extension. How do we calculate extension X? Extension is the final length of the spring. Okay, after the child, the final one, L final or L2, minus the original length, or the L1, the original length. Okay, so this is for the extension. So this will be 33 minus what? Minus 40. Right? From a length of this to a new length of this. Okay, minus 40. So this will give us a negative number 7, right? We'll get a negative number 7, right? So, or we say 40 minus this, we get, because in the extension we don't need to have negative. So we have 7, right? 7 centimeter. This 7 centimeter we can, okay, this is our final length actually. This is our final length, the bigger number. So you say 40 minus 33, which gives us 7. So we say 7 divided by 100 if you want to change to meter. 7 divided by 100 if you want to change to meter. We get 0.07, right? If we change it to meter. Why should we change to meter? What's the point of changing to meter? Why? Because the spring constant is in, look at this, is in Newton per meter. If this spring constant was in Newton per centimeter, if this value that was given to us was in Newton per centimeter, there would be no need to change this 7 centimeter. But because the spring constant is given in meter, Newton per meter, we must change this extension that's produced. We must change this extension to meter. To change it to meter is to divide it with 100. To change centimeter to meter, you divide by 100. So if we divide this by 100, we get 0.07 meter. Now we know the extension, we know the spring constant, so we can calculate the force. The question says we should calculate the force, right? He said, what is the weight? You know weight is the force, the weight of the child. They want us to calculate the weight. So we say, remember, F is equal to what? Kx. F is equal to Kx, right? F is equal to Kx. X is the extension, and K is the spring constant. So we put the value 4,900 multiplied by x, multiplied by the value of x, which is 0.07. So we multiply this by this, we get there 343. We get 343 as our weight, as the weight of the child. 343 Newton as the weight of the child. Is that okay? So you can see how this plays out. How we use this. That some cases they ask us to calculate the spring constant, but this question is asking us to calculate the force by giving us the length, the original length, and the final length. So you subtract, you get an extension. Then you convert to, based on the unit of the spring constant, what the is it in meter, Newton per meter or Newton per centimeter. So since it's in Newton per meter, we must convert the extension to meter. You must convert it to meter. And that's how we got this for the Newton as the force or the weight of the child. Is that okay? Now let's go to an experiment. This for paper 6 now. We finished what can be asked in paper 2 and what can be asked in paper 4. Now let's go to what can be asked in paper 6. You know, physics is in 3 papers. You have to do paper 2, multiple choice, paper 4, structural theory questions, and paper 6, alternative to practical questions. Now let's go to how they can ask a question here in paper 6. Now to do this, we say investigating the spring. How do we investigate speed? First, we're going to do an experiment. Now we state the aim of the experiment. So when you are doing this, you state the aim. You write the aim of your experiment. What's the aim of this experiment? The aim of this experiment is to investigate the relationship between the force and extension of a spring. That's it. The aim of the experiment, of this type of experiment, because we're talking about Hooke's law, which states that the extension produced is directly proportional to the stretching force, provided the elastic limit is not exceeded. So what are you looking for? You're looking for the relationship that exists between the force and extension. The relationship that exists between force and extension. That's what we're looking for. Force, relationship that exists between the force and extension. So you write it down as your aim of experiment. Now, the next thing you write in your experiment is variables. You write your variables, the dependent variable and the independent variable. The dependent variable and the independent variable. Okay? Just a moment. Now, what is independent variable? Now, the independent variable is the variable you change and is unaffected by other variable. You change it, but it's not affected. Okay? The variable you change and is not affected by other variable. That's the independent variable. A good example for this experiment is the force. You know, we keep adding more weight. You are the one changing it. Other things are not affecting it. You are the one that is changing it. You change it, but it's not affected by other variable. That's the force for this experiment. So you have to state the dependent and the independent. The independent is the variable that is not being affected. It's on its own. It's not depending on other variables. It's not depending on other variables. It's not depending on other variables, right? The independent variable is a variable that is not depending on other variable, but you are the one changing it. For example, in this experiment, we are changing the weight or the mass. We are adding the mass to the spring. Every time you add 2 Newton, the spring extension will increase. You add another 4 Newton, extension will increase more. So you are changing the force. You are the one changing it, but the force is not depending on extension. Extension is depending on the force. You get it? So the independent is the force. You must take this in exam in paper 6. Because they ask you to describe an experiment on how to use a spring constant or whatever. They just give you in paper 6. You can open your paper 6 and see. Then on the dependent, which one is dependent variable? Extension. Why is it a dependent variable? Because it's dependent, the extension produced is proportional to the force. Every time you increase the force, then there will be increase in extension. If you decrease the force, extension will decrease. Meaning extension is just follow. It's just following the force. It's depending on the force. It's not on its own a variable that is standing on its own in this experiment. It's as a result of what happens to the force. If I increase the force, extension increases. If I reduce the force, extension decreases. So it's called a dependent. It's depending on something else. It's depending on another parameter. So the dependent variable is the extension. So you put that. Then control variables. Now, because in Igsce now they started to teach you all of this, right? What is the control variable? The spring constant is the control variable. Usually, you look, when you are doing experiment, which one is showing the gradient? Which one represents the gradient? For example, if you are doing experiment, electricity experiment, V equal to I arrow. You remember electricity experiment? V equal to I arrow. Okay, the independent variable is the current, right? Every time the independent variable is the current, you increase the voltage increases, right? So the independent variable is the current, the dependent variable is the voltage, the control variable is the resistance, because the resistance is the gradient in this experiment. The resistance is like the gradient because it's equals to V over I. The resistance is the gradient of the graph in electricity. Is that okay? So if you pay attention to this detail, you already got two answers in exam. One from electricity, one from mechanical, which is the spring experiment. Now the one that represents a gradient is the control variable. Is that okay? So you need to state these three variables: the independent, the dependent, and the control variable. Okay? Then now the experiment, we have to list the equipment, list the things we use and the purpose. Here they just say the clamp stand, the balls, and the clamp to apply an upward force on the spring. The ruler, what is it used for? To measure the extension of the spring. To measure, as the spring is extending, you'll be measuring the extension. You use a ruler, meter rule. The spring to measure the extension also. Then the 6 times 100 gram. This is to change to force. To change mass to force. The 100 gram hanger is to hold the additional mass, the hanger. The pointer is to read accurately, to accurately read the extension. Remember pointer when you're doing this experiment. It's very important to measure the pointer. Okay, let's move on quickly. Now here is the arrangement in the experiment. Now you put method. Other method, you draw this. You sketch this in the exam, in paper 6. Other method, you draw something like a radiator stand. This is the ruler to measure. You put this this clamp stand. You put the spring here, and then you show how you are loading the mass. First one, you load this first one, then later you add this one, later you add this one. So these are the masses that you have. This is the mass hanger. This is the hanger that is holding the mass. The hook is like a hook. The hook that is holding the mass is the hanger. Okay? The mass hanger. And this is the pointer. The pointer is to read the extensions accurately, to read the extension accurately. This is the spring itself. Okay, this is the ruler. This big one is the ruler to measure the extension, how much extension is being produced. Okay, you need to be able to sketch this in the exam in paper 6. Okay, so now let's move on quickly. Then the next thing you go to result. You go to result quickly. A table of result. In the exam, you don't need to put values here. This is the only place you can just show the masses as you load the mass. You don't need to put any variables. You just need to put mass, force, length 1, length 2, length 3, and average length, and then you put the extension. Why we need to do length 1, length 2, length 3? In order to find average value. To find the average is this plus this plus this divided by 3, you get the average. This plus this plus this divided by 3, you get the average. This plus this plus this divided by 3, you get the average. This plus this plus this divided by 3, you get the average, right? You get the average mass. Now, if you want the extension, probably you use the two length. This one minus this one, you get the extension. Or the final one minus the original one, you get the extension. Like that, you get the extension. But in the exam, in Igsce, the table, you are not asked to fill the value up. They will just want to know whether you know how to sketch a table like this for this type of experiment. You put the mass, you put the force, you put the length 1, length 2, length 3, average length, then you put extension, you draw a line like this, you put the units on top. Mass, you must put /kilogram. They know you know the unit. Force, you must put /Newton. Length 1, you say /meter, length 2 /meter, because the unit of length is meter. And then average length, you say slash meter, and extension also meter. When you do like this, you get the whole mark order the table. Now you get to the result analysis. You do an analysis of the result. Here, you only play with the formula. You say the weight equals to mass times gravity. Weight equals to mass times gravity. And you show that every mass you load, you have to multiply with the 100 gram. Every mass you put, you have to multiply with gravity, the value of gravity, to get the weight. Every mass, you just explain those things. And you show each one what parameter. Then, under the analysis also, you show how you calculate your extension. You say your extension is equals to final length minus original length. Extension is what? Final length minus original. You just show it other result analysis. Even if you don't write all this story, but this one you see I'm circling, they're very important. The formula and this one, how you calculate your extension. And then you say the next, you plot a graph of the force on the vertical axis and extension on the horizontal axis. You draw the line of best fit to represent the Hooke's law. You draw a line of best fit to represent Hooke's law, and so on and so forth. Then you sketch the graph like this. You sketch the graph. Force here per Newton, extension here per meter, you sketch the graph. Because this one usually like 7 marks. Okay, usually 7 marks. Is that okay? So this is for paper 6. This is for paper. That's for the experiment. You get your marks. You can put conclusion that in the end we observe that the force, when the force increases, the extension also increases, as long as the spring has not exceeded its elastic limit. Is that okay? So now let's quickly, we are rounding up the errors. In exam, they always talk about error. What are the errors that are found in practical, in paper 6 also? One, you have systematic errors. What are systematic errors? And random errors. These are the 2 errors you discussed. Systematic errors and random errors. Now let's quickly take a look at that. Systematic errors and random error. Systematic errors are the faults in the apparatus, not your own fault. The fault that you cannot avoid. They are there based on the manufacture of the apparatus. No matter how slightly it is, even if it's 0.001 deviation, it's not your fault. They are the faults that are found in the apparatus or in the experimental method, which consistently affect every measurement that you are going to make in there. So, but what the examiner will look at, even if there is a small 0.01 deviation from the original answer, they will see how consistent your work has been. If it's consistent, then they will give you the marks because it's just a systematic error. Now, the second error in any experiment is the random error. Because if they ask you in the exam, what are the things that make your answer not to be 100% accurate? You talk about the systematic error that may be found based on the apparatus. You talk about the random error. The random error are the unpredicted changes in the experiment, causing one measurement to differ slightly from the next one. Unpredicted changes that may happen during your experiment. They are the random error. Now let's quickly talk about the safety. You know, in every experiment, you have to be careful in order not to incur accident. One of the things when you are doing experiment, you have to wear goggles. You have to wear what? Goggles. Because in the exam, when they ask you about safety, you should be able to talk about safety. You know the good thing about practical, this wearing goggle, every topic, whether you are doing electricity or you still talk about the same thing. You wear goggle. Whether you are doing mechanics, you talk about goggles. You understand? Every topic, light experiment, speed experiment, whatever experiment is the same thing. So that's why they are, even the errors, the same thing, random error, systematic error. So it makes it easy for you to remember, right? You have to wear goggle, you have to stand up while you are doing experiment, don't be seated, don't be lazy while you are doing your nerves. Your nervous system must be up and doing. You must be very sharp. Your brain, your heart, your eye. You cannot be feeling sleeping. You cannot place a mat or a soft material below the masses in order not to damage or cause any distinct. No, in this regard, you place a mat. You place a mat on if you are doing this experiment, like a thick mat below the experiment in case the mat fall down so that it doesn't break. You can say as a safety measure. You can use a G-clamp. That's what they call a G-clamp. It ensures the holding of the equipment very well. Okay? So these are safety measures you can take. So with this, we come to the end of our today's class. Thank you for joining us.